I'll be teaching stuff next. That's not a problem. So yeah, I teach structural analysis like every fall. That's like clockwork. So this is the class that's a little sporadic. So I will probably be teaching CE 321 next fall. So okay. All right, let's get started. Lecture 36. We got a celebration on Friday on centroids, trusses, and shear and moment diagrams. So just everybody's, just to clarify housekeeping for everybody so that everybody's aware. We talked about this a little bit before I hit the record button, but you all turned in homework 6.4 today. You don't have any more homework till next week. That homework I'm going to assign on Wednesday, due Friday. Okay? We do not have class on Friday next week. Okay? I'm giving you the day off. Okay? But I am going to have you turn the homework in that Friday. And the reason why is because I want you to have a break. And I want you to not have to worry about this class. We will come back, review for the final when you come back. Okay? But I imagine that you have classes that your professors are like, ooh, I have a week to give you a project. And I saw some really bitter faces in the crowd. So we're not going to do that in here. So I figure if I put you through this daily homework hullabaloo, the least I can do is give you a week off. So, all right. Everybody get the code. All right. So let's go through the exam review. Okay. So a couple things about the exam. The exam is the same format as the others. I'm not suddenly making it a different exam. There are a couple things that I think are noteworthy about this exam, at least two that come to mind. The first is you do not need to waste space on your formula sheet with the centroid of a rectangle or the centroid of a triangle or a semicircle or any of that. The handout or the page that's in the textbook and the one that was in the slides is going to be given to you on the exam. So do not, I'm not telling you not to put stuff on the formula sheet that you need to be able to reflect your understanding of centroids, but don't waste your space on the formula sheet with those regurgitated tables from the textbook. I'm giving you anything that you need there. The other thing that I think is worth mentioning is I've been saying this for the past few exams. I think this exam is the one you really should try and bring a straight edge for shear and moment diagrams, things like that, because you're going to be drawing stuff. Just spoiler alert, okay? Now, I'll go ahead and tell you a couple things that I've done on the exam, and this is as a means of making your life easier. So, for example, centroids. I would tell you there's going to be a problem where you need to compute centroid locations, and I've given you a blank table. Table space. So you don't have to draw a table. I'm trying to save you time. The other thing is if you have to draw a shear and moment diagram, I'm sort of giving you the space to do it, so that you don't have to do that. I don't want you to have to waste time on that stuff, okay? I want you to just sort of get to it. Make sense? Okay. Sorry. Let's talk about the exam and what's on the exam. We have two main topics, but I guess you could really say three main topics. And this is probably the most modular of the three exams we've had so far, and that is that we have centroids, and then we have trusses, and then we have shear and moments. And I'd say, unlike the last two exams, these really are different topics. They're centroids is sort of different than trusses. Trusses is different than shear and moment diagrams and what have you. So you need to be able to, so here's what the exam is. So the centroid, be able to compute, locate the centroid lines, areas, and volumes, and make sure that you can compute the moment of inertia of an area. As for structural analysis, you aren't going to be able to get around computing support reactions. This exam is not intended to be a repeat of exam 2, but you can't analyze a truss without computing the support reactions. You can't draw a shear and moment diagram without having the reactions. So you need those, okay? But the star of the show is being able to compute the internal forces in truss members using the method of joints or the method of sections. And make sure you can draw shear and moment diagrams for the loadings that we've discussed in here. So what I'm not going to do is say, here's a beam with a sinusoidal loading. The load is e to the x whatever. Draw the shear. I'm not doing that. It's concentrated loads and distributed loads, what we've been doing in here so far. And then the rest of this is just the greatest hits of what we've had in the slides over the past few lectures. So our definitions of moments of area, the 2D centroid references. This is what I was saying I was going to give to you. Any of these that you need, or it might just be a copy and paste of literally this on the exam, but I'm not going to make you waste space on your formula sheet with this, okay? Let's see. 3D centroid references, if you need that, I'll give you that. The moment of inertia, this is how you compute the moment of inertia of a composite shape. Again, parallel axis theorem, pretty straightforward. And again, any references that you need for that will be given. Method of joints, remember you can solve a truss one joint at a time, but the joint must contain no more than 2 unknowns, because at a joint, you have a concurrent force system. All the forces are all going through the same point, okay? Method of sections, it's a little bit more laborious to draw, but you can solve for 3 members at a time. Our relationship between load, shear, and moment, and then really the conclusions for the graphical approach, and really what that led to is how we deal with concentrated loads and how we deal with distributed loads. And that's the exam. Like, that's what's on the exam. I figure the best way, well, first off, I mean, this is your time. You can ask whatever you want. But I do think that the best way of probably handling this is to handle this like one topic at a time. So let's exhaust any questions we have about centroids and then go from there. And just so everybody is aware, I kind of thought trusses was going to come up. So I have an example truss problem that, in case we want to go through it. But if we're going to do this, I'd rather exhaust centroid and shear and moment problems first, like those questions first, and maybe we'll do this at the end. So let's start with centroids. How are we feeling about centroids? Any questions, any concerns, anything that we talked about that didn't make any sense? You tell me.
Like from 5.1, should we be concerned about like deriving those expressions?
No.
Okay.
I'll just go ahead and tell you, no, I'm not worried about it. Now, you might get some conceptual questions related to that, but this isn't Math 229.
So just these charts like this, we don't need those on there?
Not on your formula sheet. Okay. I will give you any charts like that you need. And by charts, it could be 2D centroid references, 3D centroid references, moments of inertia. I do not want you to waste space on your formula sheet with that. Now, let me qualify that, though, with one thing. It's probably not a bad idea to just sort of know that the centroid of a triangle is 1/3 of the way from the right angle on either end. That's probably not a bad idea to know. Just like it's not a bad idea to just know that the area of a circle is pi r squared. You know, I mean, it'll be on the sheet, you know, but it can help to just sort of know some things. So yeah. But I don't believe that engineers operate in a world where they can't have reference to stuff like that when they need. You know, so I have no problem with you having that on the exam, which is why, I mean, I'm letting you have a formula sheet, but I don't want you to waste your space with stuff like that on the formula sheet. So. And I'll go one further. If I don't give you a table, you probably don't need it. You know. Any other centroid questions? Okay. I'm going to peer into the crystal ball a little bit and skip trusses because, again, I've got an example. So let's talk about shear and moment diagrams because that's probably the most present in your heads right now, especially since you just did one. How's everybody feeling about shear and moment diagrams? Is that comfortable? Is there any questions? Anything you're like, I didn't get that? Yes?
Can you do like some more examples of like the different graph behaviors of when there's a distributed load?
Sure. We'll do a quick one, and I will just sort of freeform this one. So we'll do a quick one and see if I can just sort of come up with one that I think is going to make sense. All right, so Okay, so let's see. I'm sort of making this up as I go. All right, and then we'll go with let's go with that. I just made that up. Is that good? I think that'll work. Okay, so let's put some names on this. Okay, so we'll call this point B, point C, point A. And let's just knock this thing out. Okay, so I'm going to compute support reactions here and support reactions here. We'll call this CY and AY. Okay, and I'm going to do this part pretty quickly. Okay, and now, by the way, this is your review session, so if there's something I'm doing here in these calculations that you're not getting, like, you stop me and you tell me, wait, I don't understand why you did this. Okay, so what I'm going to do is for reactions, I'm going to collapse that into a single point load. And so this is going to be 2 kips per foot over 40 feet. So this is 80 kips. And then from here, that's going to be 20 feet. Right? Okay. So if I sum moments a day, all right, so if I sum moments at A, here's what I've got. I've got 80 times 20. And that's going to be negative minus 30 times 40. Let me drag this over a little bit. Plus CY times 60 is going to equal 0. All right, so I'm going to have 1,600 and 1,200 is going to make 2,800. So 2,800 foot kips is going to equal CY times 60. So CY times 60, or sorry, CY is going to equal what? Might need some help with this. Again, I literally just made this problem up off the top of my head. So 22.67. So do I have a second?
No, 46.6.
46.67. Do I have a second on this?
Yes.
Okay. All right, so we'll say CY is 46.67 kips, and we will get rid of that. And then summing forces in the y direction. So AY plus 46.67 minus, what is that, 110 kips is 0, because we're going to have 80 and 30 going down. And so AY is going to be what? It's going to be 110 minus 46.67. 63.33.
Yep.
Okay. Everybody okay with that? Yes.
This might be a little bit of a stupid question,
No, go.
but what does it mean if, can AY be negative?
Yeah, absolutely. It can be negative.
Okay.
I'll give you an example of where it is negative. Here's an example of where it would be negative. I'll just stick this down here. This would be an example of where this reaction would go up and this reaction would have to go down, because what we're basically looking at is a diving board, okay? And so if you're standing out here, like imagine the diver's flexing it, this has to hold it down to keep it from turning over.
I think last night's homework was.
That's possible, yes. So yes, that could happen. It might not on the exam. I know what you're at. You're going to ask, like, maybe. I made the exam like 2 weeks ago, so I don't even remember.
How long did it take you to do?
Like 15 minutes, 10, 15 minutes, something like that. Again, I use a rule of 3. So what I'll do is I'll make the exam, and then I'll do it like a few days later, so I've kind of forgotten what I put on the page, you know, because if I make it and do it, like I know it's not a fair, you know. Okay, I mean, it's not perfectly scientific, but it seems to work. Okay, everybody with me on this? Okay, so we're going to do shear diagram first. Okay, so we start at 0, go back to 0, hopefully. So we start at 0, then what do we do?
Go up 63.33.
And then if we go up 63.33, now here's something that can help. How much do we go from here to here? How far down do we go? 80. I mean, we're going to have a jump here, but we go down 80. But is it like that? No. We ignore this because that was just a construct to make this part easier. So we're at 63.33. We jump down 80. What does that put us at? If we're at 63.33, we go down 80. Negative 16.67. So something like that. Then a sudden jump to negative 46.67. Go over, back up to 0. Does everybody see that? So how are we feeling about this? I don't want to move on if this wasn't clear. Yes?
The only question I have about this is, I've forgotten how we find the area, like how the triangle goes down under. Like,
Oh, we're getting to that.
Okay.
We're getting to that's the next part. What I don't want to go to that if we don't know how to just get here. So, are we all good with this? Okay. So, let's integrate, and I'm going to go from right to left. Like, let's not ignore the low-hanging fruit. So, what's the area of this going to be? It's going to be 46.67 times 20. And keep in mind, this is really 46 2/3. You know, so if you want to track decimals, you can. But I mean, there's going to be some error there. So, what is that? Negative 933.4, or I mean, if we want to go like negative 933.33, because we know that's what it's going to be, right? Okay, now this part, okay? So what we're going to do is we're going to say, okay, we've got a triangle here and a triangle here. Now, by the way, what's this total distance from here to here? 40. So this plus this needs to be 40, right? Okay. So the way that we're going to do this is we're going to take the magnitude 63.33 divided by 2. And this is going to be 16.67 divided by 2. Now, by the way, why am I dividing it by 2? That's the slope of this line. The slope of this line is the magnitude of that load. Okay? So if I take 16.67 divided by 2, I'm going to get something like 8.33. And if I take this divided by 2, I'm going to get what, like 31.67? Am I right? Yeah, the 2/3 and all that. But does this work? Like, what is this plus this? 40, right? Again, I'm just sort of like, I'm knowing it's going to be like 2/3, so I'm just trying to make the point there. But again, when you're doing the exam, if you're like, if you're off by a decimal point or two, no big deal. Okay, so now let's do some areas. So how do we get this little triangle right here? 1/2 base times height. So what is that? Basically 8.33, right? 8.33 squared. Anybody got a number for me? For this this little triangle right here? Negative 69.39. Do I have a second?
I got negative 69.43.
This is close enough. We'll go with this. What about,
0.47, but same thing.
how about this? We're going to go with 69.4. There we go. I think we can all sort of coalesce around this. What about this one? And I think I'm going to be consistent and say we're just going to go to 1 decimal point on this one. $1,002.99. Like, is that right?
Yeah.
Okay, let's do a check. When we sum these, what do we get? Like, what happens when we add all these together? What do you get? Is it close enough to 0? Is everybody getting 0 on that? When you add those 3 areas together? Close enough. And again, the error is probably just due to rounding. Sound good? Okay. So now, I'm going to go ahead and erase this just to not confuse this. Okay. Just to track this with what's going on above, this is point A, B, and C, right? And then I'm going to draw an additional line right here, okay? I'm going to draw an additional line right there. Right there. Okay. Y'all starting to see why I said a straight edge would be a good idea? Okay. So we're going to start at 0. And let's follow our values. So we're going to go up to, what is this, 1002.9? Then we're going to drop down to what? What's 1002.9 minus 69.4? Should be this, or close to it.
933.4.
All right, so yeah, so it'll basically be around 933.3 or 0.4, what have you. And then this is going to drop us back down to 0, right? Again, rounding. I'm not worried about it. Okay? What does the region look like from B to C? From here to here. A line. This is a straight line. And the slope is negative 46.67. All right? Make sense? Okay. Now, just to sort of make the point for this linear region, okay? So how about this? Was that right? That the load was -2? That was the distributed load, right? Because between A and B, we had a -2 kip per foot load, right? So V integral of that. And then moment is that, right? That's what I learned in Calc 1, that if I integrate a number, I get a line, and if I integrate a line, I get a parabola. Is the x squared positive or negative? And I seem to remember that when I graph parabolas right here, when I go back to algebra or calculus and I graph a parabola that has a negative x squared term, it opens downward, right? Okay? And remember how this is the, this is where the slope equals 0 because that's where it intersects. So our moment diagram looks like that. What do we think? How are we feeling about that? Does that help?
I was confused about like the one on the homework last night, how it was like.
Do you have the problem?
Negative. Yeah.
Let's see.
How it like started negative and sloped more negative.
So so it's the same idea though. See, so let me may I borrow that?
Yeah.
Okay, so I'm gonna borrow this. All right, so it would help if I had this. Okay, so on the homework, all right, so, okay, so you had a beam, and we won't really worry about the values. The values don't really matter. You had this, right? And you had that, right? Okay, so first off, this reaction goes like that, that reaction goes like that, okay? So what happens is, so again, first off, let's just remember that W is negative everywhere along the beam, right? So what I'm saying is that shear needs to essentially do this, like it needs to go down like that. Granted, there's going to be some jumps where the reactions are, and the moment needs to do that. It needs to curve downward. So the shear diagram does like it jumps down, then big jump up, goes down a little more, jumps back down. That's generally what it looks like, okay? And then the moment diagram is really just going to go that, because both of these are downward parabolas. They're both opening downwards. You see what I mean?
Yeah. Thank you.
No problem. Like, it doesn't matter. Like, yeah, so it does go lot to a little because the slope goes lot to a little. But I think the one thing to keep in mind if you get confused is just this, right? Like, drawing it this way would be an upward parabola. And that wouldn't be. That wouldn't
So you just
comport
keep
with
the shape and translate it.
Yeah, that's basically it.
Thank you. That makes sense.
What I'm saying, here's what I'm saying. I'm saying that, see this equation? I'm saying that on this problem, the C1 and C2 would just be different here and here, but it's still the same shape, you know?
Got it. Thanks.
Did this help?
Yes.
Sound good? Okay. I did bring a truss problem if you'd like to go through one. And you're like, let's do it. Okay. I'm earning my paycheck today. This is good stuff. Well, this is good stuff. truss that I came up with. Okay. So let me make this a little bit better scale. Okay. And like that. Okay, so this is going to be our truss, and the supports are going to be over here. So this is sort of like a truss for an awning or a canopy or something like that. And we've got ten kips here and 10 kips here. And one thing I'll say, I'm sure some of you are like, what's with all the US units? How come no metric? Does the units really matter in terms of the process? Like, that's the thing about statics. Like, it doesn't really matter all that much. So, okay. In terms of dimensions, this is 12 feet. And these dimensions, I can do better than that. These dimensions are 5 feet. Okay? And so, by the way, does anybody recognize this triangle? If this is 5 and 12, what this is? 13. Okay, so you can sort of see what I'm getting at there. In fact, every diagonal is a 5 on 12 triangle, every one of them. So, like, and then I need some joint labels. So let's go with A, B, C, D, E. Okay. And then I'm going to scooch this over just a little bit so that I can do some analysis. Okay. All right. So, okay, a couple things. All right. Everybody with me so far? Everybody can sort of get the structure? Okay. All right. So, I want to make a couple points that have nothing to do with truss analysis, but this is important. Okay. How many unknowns do I have here for reactions? 1. In which direction is it? Well, no, it's a roller. Okay, here we go. So it's a roller, but because the roller's facing this way, the reaction has got to go like this, right? Okay? This one is going to have that and that, right? Okay. The first point I want to make is, okay, which one do you want to solve for first? Which one might be an easy one to solve for? Well, okay, a lot of you are saying A. I'm glad we're talking about this. Okay, so let me walk you through what my thought process is. What is EY got to be? How much force do I have going down? 10 kips and 10 kips. How much force do I have to have going up? 20. So, if I sum forces in the y direction, and we'll assume EY acts upwards, EY minus 10 kips equals 0. So therefore, EY is 20 kips going upward. Okay? Does that make sense? Okay. All right, before I state my next observation, I want to be clear. Does that make sense? how many of you are thinking, well, these two are 0 then? No, they're not 0, okay? All that you know right now is that this and this are equal magnitude, opposite direction. But you don't know whether or not they're 0, okay? The only way to determine what they are is to utilize our other equation of equilibrium. Let's sum moments, okay? Now what I'm going to do is sum moments at E so that I don't have to deal with all this and just solve for the reaction today. It doesn't really matter. We're going to sum moments at E. That is, I can do better than that. Okay? So let's sum moments at E. So let's deal with the forces that I know. So I have 10 times 12 and 10 times 24 that are both negative. Negative. Okay? So in order, because at E, these both produce clockwise rotation. So in order to produce counterclockwise rotation, I propose AX needs to go like that, right? It needs to go to the right. So this is plus AX times 10, right, from E. So 10 times 12 is 120. 240. .36 kips to the right. So if that's the case, and I sum forces in the x direction, what's EX? Or 36 kips to the left. Do that better. EX equals. Okay. All right. I did that part kind of fast, but is that clear? Yes.
Can you go over how AX is to the right again?
Okay. So if let me do this. Let's do that. Okay. So if keep your sort of finger like here at E, okay? Let's just look at the red loaves. This is going to rotate that way, right? This is also going to rotate that way. These two forces aren't going to rotate point E at all because they're going right through them. So this and this is causing clockwise rotation. The AX has to cause counterclockwise rotation because the sum of the rotations has to be 0. Does that make sense?
So AX would cancel out the moment of being
Yes, because it's the only thing that can. There's nothing else on the structure that's going to prevent E from rotating other than this reaction. See, if we didn't have a roller there, the structure would be unstable. It would just be moving. So, yes.
Okay, this is also kind of a stupid question, but when it's the little triangle on the circles, is
Yes.
that a roller?
That's a hinge.
Okay.
I'm just using the little circles to indicate a truss joint.
Like for this one, it was like triangle.
Zoom in. One at A is a roller.
That's a roller?
Yes.
Okay.
That's a hinge.
Okay.
Yes. Yes, so to fill in everybody here, if the book does this, that is that. Because both this and this can move that way. So that's why I just do that. I think it's easier. So This is good stuff, though. Any questions? Everybody good? Okay. All right. So I'm going to solve this structure utilizing the method of joints. Okay. So here's what I'm going to do it. This is the way I'm going to do it. I'm going to sort of use, like in AutoCAD, I'm going to use the explode command. And so I'm just going to separate everything. Okay. So what I'm going to do is I'm going to sort of draw the truss like this. Hold on. Okay, so I'm splitting the truss apart, and what I'm basically saying is I've got like, so we'll just draw these sort of dashed lines. Bear with me for a second. So instead of doing a joint at a time, I'm going to do all the joints all at once. So we'll do that, 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 that. You can kind of see what I'm doing here. Do better at this one. Like that. Okay. So by the way, let's not forget this. Okay? Let's not forget that every diagonal is at a 5 to 12 slip ratio. Every one. Okay? So the point I'm making with this is that if I know this component, I can easily figure out this one. Okay? Does that sound good? All right, so let's start filling in some information, okay? So what I'm going to do is I'm going to be color-coded here. I'm going to use the color red for anything that I know going into a joint analysis. And so the first thing that I'm going to do, 10, 10, 20, 36, 36. Okay. And while I'm at it, let's go ahead and name the joints. So let's see, A, B, C, D, and E. Okay. All right. So now let's do a solution strategy. Let's figure out what order do we want to solve our joints. Do we want to solve this joint first? We can't. Why?
There's more than two.
Exactly. There's 1, 2, 3, 4 members framing through joint D. We can't do that. We can't start at B or A, right? But we could start at C and E. We could do either one, right? So let's just do those first. So let's do C first, then we'll do E. Okay? Which one do you want to do first? C or E? Doesn't matter. Pick one. C. All right. So C is going to have this and a horizontal and a vertical. Any diagonal we can split into X and Y components. Any horizontal or vertical is just going to have one, right? Is that okay? Okay. So help me out. How many unknowns do we have here in the horizontal? 2. How many vertical unknowns do we have? So if this is 10 down, what's this? 10 up. So this has got to be 10 up. Okay? Now, everybody watch up here. If this is 10, how do we know what this is? So how about this? This is the vertical, right? So 10 is to 5, as something is to 12. What's that something going to be? 24. Does everybody see that? I want to make sure everybody saw that. Right? Because, like right here, if this is 5 and 12, and this is 10, I double that and I get 24. Do you all see that? Okay. So if this is 24, what's that? If this is 24 to the left, what's this? 24 to the right. Does this joint meet equilibrium now? Yes. 24 to the right, 24 to the left. 10 up, 10 down. The joint's in equilibrium. Done with that joint. Now, before we move on, okay, I want to do something, okay? I want to transmit my results to the next joint. This is 24 to the right. So over here, what do I put? So 24 to the left. So let's do that. So I guess my question is, let's go with our plan, but could I go ahead and solve joint B right now? I could, right? But we're going to stick to the plan, okay? But I also want to do this one, okay? So I have 24. $10. Does that make sense? Okay, let's go to joint E because that's the order we said we were going to do it in. Okay, joint E. Horizontal, vertical, vertical. Tell me what to do.
Down gonna be 20.
Well, hold on. How many verticals though do we have? How many horizontals do we have? So, what does the horizontal have to be? 36 to the right. Okay. All right. So how about this? Let's look at our little pattern here. If this is 36, what's that? 15. So that makes this 15 going down, right? You see? 5, 10, 15, 12, 24, 36. See that? So, all right, now let's put our thinking caps on. What is this vertical going to be? Let's see. We've got 20 up, 15 down. What does that have to be? 5 down, right? Y'all see what I'm doing here? So let's transmit the results. And I know we're running out of time, so we won't be able to finish this, but see what I'm doing? Anytime I solved that joint, I transmitted those results to the next one. But see how we're just working it through? I think that you should finish this on your own, but I want to say 2 things, okay? First off, I think you should probably do joint B, then joint A, because, I mean, you could do either one. So are you ever actually going to have to analyze joint D? But what will joint D serve for? What will it be? It'll be a test or a check. Because if you look at joint D, there's a lot going on, but everything going to the left should equal everything going to the right. Everything going up should equal everything going down. And one last thing before I let you go. Member BC. Let's look at member BC. It's got 24 kips. Tension or compression? Compression, because the forces are pushing on the joint. Here's my marker, here's my hands. If I push compression, what's the marker doing? It's pushing on my hands. The member is pushing on the joints, it's pushing back. That's what these forces are doing. This is the pushback, right? Member AE is in, now hold on, member AE, tension. Because if I have a rubber band and I pull on it, if I pull on it, what's the rubber band doing? Pulling back. These are the pullbacks, the pushbacks, okay? Does that make sense? Did this help?
Yes.
Okay. Does anybody have any questions, quick ones?
So for the 5/13, does that work when there's not multiples of 5/13?
It does. You just have to do like a slope ratio. So like if this was, 1, right? This would be 12 over 5. So yeah, it'll work. You just have to slope ratio it out. So you say 5 over 12 equals, something over 23, whatever it is. So yes. Sound good?
Can you post the answer?
I will. I'll post it tomorrow. Not today. The answer to this. That's all I got. I'll see you. I'll bring up the code one more time.